Hello students, welcome to Vassiversity. Today we're going to start talking about implicit differentiation. So previous lessons we were only dealing with explicit differentiation and explicit functions. Right, so explicit is essentially when we have y of f of x. Right, so y is on the left side, f of x is on the right side, they're both separated, they are not mixed. Implicit functions are those functions where y is equal to f of x, y. Right, so for example, and let me actually give both examples. So we have y equal to square root of x cubed plus 1. Right, this is an explicit function. And then implicit function would be something like y cubed plus x cubed is equal to 6xy. Right, we cannot quite solve sometimes directly for y and express it in terms of x because it's too nonlinear for us, right? So that's when we come to go to the implicit differentiation. So essentially, what implicit differentiation gives us, it gives us slopes, right? Implicit differentiation essentially consists of differentiating both sides of the equation with respect to x and then solving the resulting equation for y prime. Okay, so for example, if we have y squared, right, how do we find the derivative of that? Well, we have to use a chain rule, right, if I want to find a derivative. So by the chain rule, we're going to have the derivative of y, right, which is the internal part. So, but what's our outside function? Our outside function is a square function. So it will be 2 times y prime, right, by the chain rule. We do not know what y is, right, but we just implicitly differentiated this function, right, because y itself was nonlinear. Okay, so let's go ahead and take a look at it. So the most important part about it is that application-wise, we are able to find rate of changes of a certain functions. For example, we have a function x squared plus y squared is equal to 25, which is a circle with the radius 5, right? And so we want to find, essentially, dy dx, right? Or, which is equivalently y prime. Okay, so what do we gotta do here? X squared plus y squared is equal to 25. We gotta go ahead and take the derivative of the entire equation. Right, so we know the properties of the derivatives that we learned in a few lessons ago. So we're gonna have d dx of x squared plus d dx of y squared is equal to d dx of 25. All right, perfect. So notice that immediately here we have the question, right? And most of you might ask the question, well, how do we differentiate that? By chain rule. That's why at previous lesson we learned the chain rule. So now we can use it and apply it for this problem. Okay, so derivative of x squared by using the power rule is going to be 2x, plus by using the chain rule is going to be 2y times dy dx is equal to the constant, right? So derivative of a constant is 0. Okay, so this is our function here. So that means if we solve for dy dx, so we're going to have 2y times dy dx, which is the rate of change, is equal to negative 2x, right? Dividing both sides by 2y. 2y goes away, 2 and 2 goes away. So that will give us dy dx is equal to negative x over y. And so what is dy over dx? This is rise over run. That's a slope, right? This is a slope of x squared plus y squared equal to 25. And this is a function. So now, if we have a circle, right, we can plug in any point, right, any point on that circle, and we will know, right, we will know the exact slope at that point on the circle, right? So that's why it's so important. And that's the physical application for the implicit differentiation. Okay, now let's go ahead and find the following, right? Let's go ahead and actually do another example. So let's say again, we have x cubed plus y cubed is equal to 6xy, right? And we asking to find y prime. Okay, so what does that mean? That means we're going to again take a derivative of the entire expression, right? But this time the right-hand side is not a constant. So that means we're going to have x cubed prime plus y cubed prime is equal to 6xy prime. Ready? So let's differentiate it. So this is actually this is going to be part A. Okay, so we're going to have 3x squared plus, by using the chain rule, it's going to be 3y squared times y prime is equal to, by using the product rule, it's going to be 6xy prime plus 6y. Okay, now our goal, right, our goal is to solve for y prime. Okay, but before that, let's go ahead and divide the entire equation by 3. So we're going to have x squared plus y squared times y prime is equal to 2xy prime plus 2y. Okay, let's go ahead and move all y primes to the left and the rest of the stuff to the right. So we're going to have y squared times y prime minus 2xy prime is equal to 2y minus x squared. Now, let's go ahead and factor out. So we're going to have y squared minus 2x times y prime is equal to 2y minus x squared. Alrighty. Now let's move on here. So we're going to have y prime to be 2y minus x squared over y squared minus 2x. Okay. Then part B. Part B is asking us to find the tangent. Find the tangent to x cubed plus y cubed is equal to 6xy, which called a volume of the cartist. So at the point 3, 3. Okay, which means what? X is equal to 3, y is equal to 3. Okay, that's important. Because, well, how can we find it? We have to plug that in. Right? We have to plug that in. We have to plug it into this equation. So what are we going to have? So again, y prime is equal to 2y minus x squared over y squared minus 2x. So we're going to evaluate it at 3, 3. So that's equal to 2 times 3 minus 3 squared over 3 squared minus 2 times 3, which is equal to 6 minus 9, 9 minus 6, which is equal to negative 3 over positive 3, which is equal to negative 1. So that is a slope, right? This is a slope at the point 3, 3. Okay, so then by using the equation of a line, we will have, so part C, right? Or actually, no, that's still going to be part B. So it's going to be y minus 3 is equal to the slope, which is negative 1 times x minus 3. So if we solve, we're going to get y is equal to 6 minus x. All right, perfect. So let's go ahead and take a look at the picture, at the graph of this line. So this is how it's going to look like. Right, this is our x cubed plus y cubed equal to 6xy graph in blue. And a red line is our slope at the point 3, comma 3, right? We always have to make sure that the point actually is on the graph, right? We can't just pick an arbitrary point. Okay. So then, interesting thing is for part C, right? So now we can see the graph, right? We can see the graph, and part C will ask the following question, right? Interesting question that oftentimes is important for applications. At what point in the first quadrant, in the Q1, right, first quadrant, is the tangent line horizontal? Right, what does that mean? That means that the slope is equal to 0. Okay, so at what point? Well, of course we have to go ahead and equate y prime, which is equal to 2y minus x squared, over y squared minus 2x is equal to 0. So we are assuming that we're not dealing with 0, 0. So we will have, so we assume that y squared minus 2x is not equal to 0. And we will get that 2y minus x squared is equal to 0. Which will imply that y is equal to 1/2 x squared. Okay, so now let's go ahead and plug in. Right, let's go ahead and plug in. So, plugging that in, we're going to get into the equation. So x cubed plus 1/2 x squared cubed is equal to 6x times 1/2 x squared. All right, so this equation, right, going to simplify. So we're going to have x cubed plus 1/8 x to the 6 is equal to 6 over 2. This is going to be 3x cubed. Okay, so that means x to the 6 will be equal to 16x cubed. So we know that x is not equal to 0 in this case, so that means x cubed is going to be equal to 16. So we will get that x is equal to cube root of 16, which is equal to 2 to the power of 4 thirds. Okay, and then y, which is equal to, was going to be equal to 1/2 of 2 to the power of 4 thirds squared, which will be equal to 1/2 to the power of 8 thirds, and then which will be equal to 2 to the power of 8 thirds minus 1, which is equal to 2 to the power of 5 thirds. All right, so that means that our point, our final answer, is 2 to the power of 4 thirds, comma 2 to the power of 5 thirds. Right, so at that point, which is, if we zoom in onto the pedal, essentially, right, if we zoom in right here, really close, we will get that this is the point, right here. And the slope at that point, right, as we require, is 0, right? So here we have the y prime is 0. All right. Perfect. Perfect. So, some of the important things that we get from the implicit differentiation is actually we're getting maps, right? We call it essentially the fields, right? The fields of the derivative, the differentiation field, right? So we can also call them implicit plotting, right? It's used in computer algebra and computer science. So let's take a look at some of the examples, right? Some of the actual graphs, right? So if we decide to take an implicit derivative of it, right, dy dx, that's going to be the slope map, right? That's essentially the slope as a function, because we get dy dx as f of xy. This is the derivative field, right? That's how we call it. So, well, there's multiple. So if we impose some conditions, we're going to be in a very specific line, right? But only if and only if we are actually imposing some strict conditions on our function, then we will be able to find an actual answer to it, an actual specific line, and not the entire field, because this field represents family of solutions, right? So that's infinitely many solutions here based on the conditions. But if we impose some conditions onto it, we will choose a specific line, right? Specific line that will satisfy our specific needs. Okay. Now, let's go ahead and, well, consider this equation. So, this example. So we have x to the 4 plus y to the 4, which is equal to 16. And we want to find y double prime, right? So we want to implicit differentiate twice. Okay, since we've already done it multiple times, let's go ahead and do the first derivative. So we're going to have 4x cubed plus 4y cubed times y prime, which is equal to 0. So that implies that y prime is equal to negative x cubed over y cubed. All right, that's when it gets tricky, because now we got to do y double prime, which is going to be negative x cubed over y cubed prime. So by using the quotient rule that we learned a few lessons back, we're going to have negative y cubed times x cubed prime minus x cubed times y cubed prime all over y cubed squared. Okay, so that will be negative 3x squared y cubed minus, so essentially we're getting x cubed times 3y squared y prime all over y to the 6. But what is y prime? Can you guys tell me? Yes, that's exactly right. It's going to be this. We can plug it in. All right. So if we plug that in, we can actually simplify. We're going to have negative 3x squared y cubed minus 3x cubed y squared times negative x cubed over y cubed. And then all over y to the 6. Okay, so if we go ahead and simplify, right, well, first of all, we can factor out the 3. We can simplify some things. So we're going to have negative 3x squared y to the 4 plus x to the 6 all over y to the 7. And that's going to be equal to negative 3x squared y to the 4 plus x to the 4 all over y to the 7. And well, notice, what was y to the 4 and x to the 4? Remember, it was equal to 16. It was a constant. So that means we're going to have negative 3x squared times 16 over y to the 7, which is equal to negative 48 of x squared over y to the 7. So and that's going to be essentially the slope of the slope, right? The slope of the function x to the fourth plus y to the fourth. So for example, if it was a path, right? If we, let's say we were using this function as a path, as a distance path, right? Then, and we would say, let's say a car would be traveling on that path, then this equation would actually give us an acceleration, right? Essentially the slope, right? The slope of the position, right? The slope of the position's velocity, right? So if we take one derivative, it's going to be velocity. The second derivative is going to give us acceleration, right? So that's going to be acceleration. Acceleration is the speed of the speed, technically speaking. All right, so that would be a physical application of it. Now, let's go ahead and move on to the inverse of the derivatives. Okay, so inverse of the, not derivatives, of the trigonometric functions, specifically. Because last time, we also did the trigonometric functions a couple lessons ago. So now we're going to be actually doing the inverse of the trigonometric functions. Because remember, in trigonometry, we do have arcsine, arccosine, arctangent, and they are part of functions, right? But now we want to go ahead and take derivatives of them. So, the last part for today is going to be the derivatives of inverse trigonometric functions. All right. So, remember, y equal to arcsine of x, which is equal to the same thing as sine of -1 of x, which is meaning inverse, right? As after the -1 as an inverse, right? There are different notations depending on the book that you read in general. So it means, right? It means sine of y equal to x, right? For y, in this case, between -pi/2 and pi/2. Okay, so if we decide, right, if we now decide, by using our knowledge, let's go ahead and take a derivative. Implicit derivative, right? What are we going to get? We're going to get derivative of sine y. It's going to be cosine y times y prime is equal to 1. So it would be y prime is equal to 1 over cosine of y. Okay, so now we know that y is equal to sine of the inverse. Okay, so cosine of y, which is equal to cosine of sine inverse of x, is going to be equal to, by using the trigonometric identity, it's going to be square root of 1 minus sine squared of sine -1x, so meaning that inverse, right? So remember, cosine square x plus sine square x is equal to 1. And remember, the f of f inverse of x is equal to f inverse of fx, which is equal to x. All right, so here sine and inverse sine cancel out, so we are actually going to have square root of 1 minus x squared. All right, so what does that mean? That means that now we can plug in. So y prime is equal to 1 over cosine of y, which is actually equal to 1 over square root of 1 minus x squared. So that implies that dx of sine inverse, right, sine or arc cosine inverse is equal to 1 over square root of 1 minus x squared. All right, perfect. So what other easy way we could do that? Well, we could do the same thing for the tangent, right? So if we consider tangent of y is equal to x, this is actually one of the very important ones and the very common used ones. So if we take a derivative, we will have secant squared y times y prime is equal to 1, which means that we will have y prime to be 1 over secant squared of y. Again, by using the trigonometric identity, that will be 1 over 1 plus tangent square y, which is, well, if we solve, right, if we solve for the y, we know that y is equal to tangent of inverse of x. If we plug in, it's going to be 1 over 1 plus x squared. So d dx of tangent inverse of x is going to be equal to 1 over 1 plus x squared. All right, so the rest of them can also be done in a similar manner. So I'm going to go ahead and give you guys the table. This is the table of the derivatives of inverse trigonometric functions, right? The left-hand side are the most common derivatives that are used in Calc 1 and Calc 2, right? So those are worth memorizing. And it's, of course, important to remember how to derive them in case you need to derive them. All right. So next lesson, we will go over the logarithmic differentiation, and some of the tricks of implicit differentiations are needed in order for us to do that. All right, thank you, and I'll see you guys next time.